In the last class, we had started with Newton's first law of motion, and let us just recap that. The first law stated that if a body is at rest or moves with uniform velocity, which means constant speed along the same direction. So, if a body is in such a state, then the net force acting on the body is 0. This is one way how the first law of motion can be stated. Now, this law, the first law, sometimes is also referred to as the law of inertia, because inertia we say is the tendency of the body to maintain its state of rest or uniform motion. Now, we have seen when we did kinematics that a state of motion is a state which depends on the reference frame. So, state of motion, this is dependent on the reference frame, whereas when we look at force, forces are quantities which are frame independent. That means, whichever frame you measure a force in, so whether the frame is a frame at rest, frame moving with constant velocity, or a frame which is accelerating, the forces if you measure, they stay as same. So, now when we look at Newton's first law, it is saying the net force is 0 if a body is at rest or moves with uniform velocity. That means something is missing, because we are saying a frame independent quantity, we are relating that to a frame dependent quantity. And the catch to that is that Newton's first law, and for that matter even the second law, which we will see later during the lecture today, this is valid only if we are observing the state of motion from an inertial frame. So, then the question which we then say is, what is an inertial frame? So, what we are saying is Newton's law, whether it is the first law or the second law, that is valid only if the state of motion which is being observed with respect to an inertial frame. Now, an inertial frame is a frame which is at rest. That means the frame is not moving. What we have also shown is that any frame which moves with a constant velocity with respect to an inertial frame is also inertial. That means we are now widening the scope of the inertial frame. So, first we say a frame which is at absolute state of rest is an inertial frame, and then we also say that another frame which is moving at a constant velocity with respect to an inertial frame is also an inertial frame. So, that means for Newton's laws to be valid, the frame of reference which you are looking at has to be either at rest, and in that frame of reference you are measuring the velocity and the motion of the particle, or the frame can move with a constant velocity. Now, constant velocity means there are two parts, the speed has to be constant and the direction has to be the same. So, that means, so let us explain this again. So, the constant velocity, this implies that there are two things. The first thing is the speed is constant, that means the frame should not be accelerating, and the second thing is that the direction of movement should be the same. That means the reference frame should be could move in a straight line at constant speeds. So, if that is so, then the frame will be an inertial frame. Let us first give an example and then we will talk of inertial frames before we move to Newton's second law. So, let us say this is the carriage of a train and the train is at rest, and a person is standing on the train. So, now when we look at the person who is standing on the train, the person is not moving with respect to the train is at state of rest. So, now let us say frame 1, we fix the axis on ground, and frame 2, which I show with a different color, I put this as small x, y, z. So, frame 2, here we are fixing the axis on the train compartment, and the person is standing at a state of rest. So, now when the train is at rest, then both the frames, in there we observe that the person is not moving. So, both these frames at this time are inertial. Now, what we do is let this frame, let the train accelerate. So, we have this train and now this is accelerating. The person is still standing on the compartment, is not moving. So, here now when we observe with respect to frame 1, the person we observe is moving and has an acceleration a, whereas with respect to frame 2, which is the frame on the train, the person is still at rest. Now, in these cases, frame 1 is an inertial frame. This is a frame which is at rest, whereas frame 2, here we see this frame is mounting on the train, this is accelerating. So, this is not an inertial frame. So, therefore, for Newton's laws to be valid, that means when we look at this person with respect to an inertial frame, the person is moving. That means the person is accelerating. So, therefore, there has to be some force acting on this person which will cause it to accelerate. Had we looked at this person from frame 2, we would have said the person is not accelerating, so therefore there should be no force. But there has to be a force because frame 2 is not an inertial frame of reference. And just to clarify these things, if we go ahead further, let us say the train has moved for some time and the train is still moving, but now acceleration is 0 and velocity is constant, let us say the track is straight. So now when we look at it, what we have, frame 1 which I have shown as capital XYZ, frame 2 which is small xyz. So now if acceleration is 0 and train moves in straight line with constant speed, then both 1 and 2 are inertial frames. So this is how we define or we look at inertial frames of reference, and Newton's first law, which we have said, the law of inertia, and the second law which we will study, they are valid only if the motion of the particle is being studied with respect to an inertial frame of reference. Now the question which one then asks is, can we have an inertial frame of reference? So does an inertial frame exist? And why do we ask this question? We say, okay, I am observing, I am standing here, I observe this pen is moving, I have fixed my frame on the ground here and the pen is moving. So why is this frame with respect to which is connected to? So in most cases what we do is we fix the reference frame on surface of the earth, and then we ask, is this frame inertial or not? Well, we do not observe when I am standing on the surface of the earth, I do not see any motion. So it obviously looks to me that this is an inertial frame. But what we know is that the earth is spinning about its center, and so suppose if I am at the equator, then at this point on the surface of the earth, the acceleration is equal to Re times omega square, where Re is the radius of the earth and omega corresponds to earth's spin, which is one rotation in 24 hours. So omega will be equal to 2 pi radians divided by 24 into 3600 seconds. So if we work this out, then what we find is that the acceleration, when we do work this calculation, the acceleration due to the spinning of the earth, this is equal to Re times omega square, and if you look at these numbers, this turns out to be 0.034 meters per second square. So now maybe for most purposes where we want to study the motion of a cricket ball, motion of a tennis ball, we can ignore this acceleration, and if we can ignore this, then it is fine, and we can say that okay, the reference frame connected to the surface of the earth is inertial. But when we want to study the motion of currents and motion of winds, then they are moving with respect to the surface of the earth, and there this cannot be ignored. So then one says, okay, the earth's surface is not inertial, let us go to something more. So what we do is, then we say we fix a reference frame on center of the earth. So instead of fixing it on the surface, I fix up a reference frame here. Now this frame will spin along with the Earth's rotation. So therefore, we say maybe this frame is this an inertial frame. Now what we realize is that Earth is in itself in an orbit around Sun. So therefore, there is some angular motion associated and there is acceleration. So this frame is again not fixed, it is accelerating. And if we try to work out the acceleration of the frame fixed to center of Earth, and we know it is actually an elliptical orbit, but if we assume it to be a circular orbit, then this will turn out to be, if this radius is r1, it will be r1 omega 1 square, where omega 1 is equal to 2 pi divided by 365 days. So if we, let me write this clearly, omega 1 will turn out to be 1 rotation in 365 days, very small omega, but still it exists, and if it cannot be ignored, then it turns out that the acceleration of this frame, which is equal to r1 omega square, this turns out to be 0.006 meters per second square. So theoretically speaking, even a frame connected to the center of the Earth and rotating with the Earth is not an inertial frame, because the Earth itself is revolving around the Sun. So then what we say is, if we fix, so we go one step ahead, we fix a frame on center of Sun, but then what we see is that the Sun is moving around the center of the galaxy, and if we look at the acceleration of the Sun towards the center of galaxy, this turns out to be 3 times 10 to the power of minus 10 meters per second square. Much slower, but technically speaking, then maybe even this cannot be inertial. And then if we say you fix a frame to the center of the galaxy, then this again, the galaxy may be moving towards other galaxies, and if that is so, then we are not sure if an inertial frame exists, it cannot be answered. Does it mean that then all laws of Newton are not valid? Certainly not so, because then what we do is we try to see in which frame do we find Newton's laws to be valid. One thing you realize, we are using the word laws. Laws are like theory, which means we have made some postulate, and then we, if that works, then we use that theory. So therefore, we do find that for most applications in classical mechanics, a frame fixed on surface of Earth can be treated as an inertial frame. In some cases where we want to really account for the rotation of the Earth, then we use the frame fixed to center of earth is more accurate. So, normally in most problems of classical mechanics, these two frames work. As we said, when we look at typical problems of a body moving, vehicle moving and things like that, the frame fixed to center of earth will suffice. So, this was a bit of discussion which we had on inertial frames, and with that then we move on to Newton's second law. Now, as we discussed in the last class, we define a quantity called momentum, which is the product of mass times the velocity. And what the second law does is, second law relates the net force acting on a body to its rate of change of momentum. So, let us first try to look at this quantity called momentum. Now, we see momentum is defined, as we have said, as a product of mass, which is a scalar, and velocity, which is a vector. So, therefore, momentum itself is a vector quantity. Now, what we know is, if we apply, we observe this, if we apply the same force on a light body or the same amount of force on a heavy body, what difference do we observe in the motion? What we observe is the light body, this moves faster, whereas the heavy body moves slower. So, clearly force has a relation with mass. At the same time, we also realize that it is not only mass, but speed is also another factor when we want to characterize the force. Let us think of a bullet. A bullet fired from a gun, when this hits a target, it pierces through the target, or it will get stuck in it if the target is very strong or very thick, it gets stuck. Whereas, the same bullet, if I take it in a hand and I throw it on the wall, it hits lightly. And for example, if I am standing and a bullet comes and hits me, it will injure me. Whereas, if you come and you throw the bullet on me, I will not get injured. So, therefore, we realize from this that when it comes to causing an effect on my body, the speed also makes a difference. With the same mass bullet, if it is coming to me with a very high speed, it will injure me, whereas the same bullet, when it is thrown with a low speed, it will not injure me. And the effect of these two quantities put together, of the mass and the velocity, and these two effects are put together in one way in form of momentum, which we define as, we have said, as mass times the velocity. Now, also what we said was that there is a directional effect, and this comes because of the vector v. And suppose, let us think of it, that there is a string, there is a stone tied to a string, and we sling this stone. So, I take a stone, tie it to a string and move it in a circle, and let us say the angular velocity is constant. So, then what we realize is, in this case the stone moves with a constant speed, but its velocity is changing. Why is the velocity changing? Because the direction of the speed is changing. So, therefore, even though the stone is moving with a constant speed, its velocity is changing, and therefore, its momentum is changing, because the velocity is not constant, its direction is changing. And what we realize is, if we are doing this exercise, that we are taking a stone and we are moving it in a constant speed, we do realize that there is a force in the string, and that force has to be applied on that string, so that the stone can move in a constant circle. That means, even though the stone moves at a constant speed, a force has to be applied. And these things, these ideas which we discussed, they are quantified in Newton's second law. So, now let us see what is Newton's second law, and Newton's second law says that rate of change of momentum of a particle is directly proportional to the applied force on the particle, and the change of momentum being a vector quantity, since momentum is a vector quantity, it takes place in the direction in which the force acts. Now, notice this force which we are talking of is applied on the body. So, this is an external force on the body, and we apply a force on the body, and that causes a rate of change of momentum, and the rate of change of momentum is directly proportional to the applied force, and this is Newton's second law. So, now if we try to look at it quantitatively, what we get is that if suppose a force F acts on a body for time delta t, and let us say the body has a mass m, and because of the action of this force, it changes the velocity of the body from v to v plus delta v, then what we find is the initial momentum of the particle was m times v, the final momentum of the particle is m times v plus delta v. So, therefore, the change in momentum, which is delta p, this is equal to p final minus p initial. This will be equal to m times v plus delta v minus m times v. So, this will be equal to m times delta v, and what Newton's law says is that the external force which is acting on the particle, this is proportional to the rate of change of momentum. So, change in momentum is delta p. So, rate of change of momentum will be delta p by delta t, and so this will imply that force is equal to a constant k times delta p by delta t. When a quantity is proportional to something else, then this is equal to a constant times the thing with which it is proportional. So, therefore, what we do is in the limit delta t goes to 0, this becomes force is equal to k times dp by dt, where dp by dt is equal to the rate of change of momentum. Now, let us look at this quantity dp by dt. This is equal to d by dt of m times v, and if mass is fixed, which we would expect for any particle, if we are talking of a closed system, then mass will be fixed. So, then dp by dt becomes equal to m times dv by dt, and this becomes equal to m times acceleration. So, this is how we can relate the rate of change of momentum to the acceleration. So, therefore, what we get is, since f is equal to k times dp by dt, this will become equal to k times m times a. Now, what we do is we choose our units of force in such a manner that k is equal to 1. For example, we know that if we talk of SI units, then we know mass is in kg, acceleration is in meters per second square. So, and the units for force, this SI units are referred to as newtons, and 1 Newton is equal to 1 kilogram meter per second square. So, then what we say is 1 Newton is the force which causes a mass of 1 kg to have an acceleration of 1 meter per second square. So, therefore, when we choose Newton like this, then k becomes equal to 1, and we get the formula F is equal to ma. Now, some things to look about. The first thing, once again we would like to focus on is, because we are talking of acceleration here or momentum or the rate of change of momentum, when we talk of, these have to be measured with respect to an inertial frame for Newton's law to be valid. We have to measure the acceleration or momentum, whatever quantities related to the kinematics of the particle, they have to be measured with respect to an inertial frame, otherwise Newton's law will not be valid, because once again on the other side we have force, we have a law like force is equal to ma. Force does not depend on the reference frame, acceleration depends on the reference frame. So, for this law to be valid, we have to specify the reference frame where acceleration is measured, and that has to be an inertial frame, about which we have discussed in detail earlier. So, now if we try to look at some salient points about Newton's second law, the first thing we realize is, if sum of the external force is equal to 0, then acceleration is equal to 0, and if acceleration is equal to 0, this will imply that velocity is equal to constant, and that means this is what is Newton's first law. So, therefore, some people even refer to as Newton's first law as a special case of Newton's second law, whereas there is another school which says Newton's first law helps us to define what is an inertial frame, and Newton's second law is F is equal to ma, provided acceleration is measured in an inertial frame. Or some people even word the second law as saying there exists a frame I called the inertial frame, where the relation F is equal to dp by dt, the rate of change of momentum, is valid. So, this is how different people look at it. Either you look at the first law as a special case, or you say first law defines an inertial frame, and in that frame the second law is valid. The second feature, let us look at it. We have Newton's second law is a vector law. What I mean by vector law, probably not a standard term, that both the quantities f, a or p, these quantities are vectors. So, that means when mass is constant, we get Newton's second law as F is equal to ma. So, we can write we can write it as dp by dt. So, therefore, we can write the scalar components of this. This was our first law, but we can write scalar components. So, the x component, we can write it as Fx is equal to change of x momentum by t, rate of change of this, which is equal to m times the x component of acceleration the y component of force is equal to the rate of change of y component of momentum. So, we can write Fy is equal to m times a sub y, where a sub y is the y component of acceleration, and similarly the z component of force is equal to the rate of change of the z component of momentum, or mass times acceleration in the z direction. So, independently we can apply these three scalar equations. So, if we are talking of a three scalar equations, they are equivalent to the one vector equation F is equal to ma. And sometimes in problem solving this may help, because we will apply these equations maybe only along one or two components, not along all the three components. Now, the third thing which we see is that Newton's law in the form in which we have seen, this is valid for a point particle, a particle which exists whose motion is there and it is occupying a very small region in space. Now, the law can be extended for a finite body, in particular for a rigid body. But when we apply it on a finite body, one thing we have to keep in mind is that the forces which we talk of, they have to be external to the body. The forces which are internal to various points on the body will not be considered when we apply Newton's law for a rigid body. And the second thing which will come in here is that the acceleration, when we apply it to a finite body, it will turn out to be the acceleration of a special point on the body, not of all points, and this point, we will see this later, we will call it the center of mass. So, this discussion of how to apply Newton's second law for a rigid body, we will leave till we talk about rotation and rigid bodies. But it can be extended, and sometimes Newton's second law applied to a rigid body is also referred to by some people as Euler's first axiom. So, more details on this will follow when we talk of rigid bodies. But the other thing what we realize is that this relation F is equal to ma is a local relation, which means the force is being exerted at time t on a body, and it causes acceleration at that time t. So, when we write F is equal to ma, the force is applied at a time t, immediately it causes an acceleration at that time. So, therefore, in F is equal to ma, there is no sense of history of motion of the particle. Of course, if the force F is constant, is acting for a long time, then maybe we can integrate it on time. But as such, given this relation F is equal to ma, it is just a local relation. At that time, whatever force is being applied is equal to the rate of change of velocity, which is what is acceleration, multiplied by m for the particle at that time itself. Now, it also, let us look at this relation from the momentum viewpoint. We have F is equal to rate of change of momentum. So, this we can write it as F dt is equal to dp. And now, if we integrate, on left hand side we are integrating with respect to time. So, let us say we integrate for time t1 to t2, and on the right hand side we have dp. So, let us do it again, integral f dt, we integrate this from time t1 to t2, and this is equal to dp. So, this will be momentum at time t is equal to t1, and this will be momentum at time t is equal to t2, and we have a special name for this quantity, integral f dt, which means we integrate the force with respect to time. This is referred to as impulse. And if we look at the right hand side, it is equal to integral dp, which will become p at t2 minus p at t1. So, this is also written as, we can define, we have impulse is equal to p at t2 minus p at t1. So, we can say impulse of a force acting on a particle from time t1 to t2, this is equal to the change in momentum of the particle during this time interval. So, this is another way of writing Newton's second law, and sometimes if f is constant, then integral f dt will just become equal to f times delta t. And even if the force is not constant, sometimes we use an average force and we say f average times delta t, and this is what we refer to as the impulse. And the usage of impulse comes because impulse, if we know, this is equal to the change in momentum of a particle during the time interval on which it is acting. So, this in effect is essentially Newton's second law. Now, this impulse relation is particularly useful when we talk of a system of particles or two or three particles which collide. Now, when there is an interaction between two or more particles, then the interaction between two particles, suppose I have this hand, it comes and hits the second hand. So, there is a force which is transmitted. Now, there is a relation, let us say this is body 1, my right hand, my left hand is body 2. My left hand is fixed here, body 2 comes, hits this body. So, now when it is hitting, there is a force which is transmitted from body 2 to body 1, and at the same time body 1 transmits another force on body 2. What is the relation between these two forces? And the relation between two forces when two bodies interact, this is given by Newton's third law. And what Newton's third law says is, when two bodies interact, then FAB, the force that body B exerts on body A is equal and opposite to FBA, which is the force that body A exerts on body B. The two bodies, when they interact and forces are interacting between them, we represent this interaction with the forces. The forces which are transferred between the two bodies are equal and opposite. Now, what Newton had stated was the Newton's third law. If we look at some classical texts, this states that to every action there is an equal and opposite reaction. This is the classical statement of Newton's law, but in this statement, when we write it like this, action here means force exerted on body A by body B, and the reaction is represented as F of BA. But because this has been put in words like action and reaction, this has led historically to a lot of confusion and misconception. The misconception, as we see, that basically this gives a sense of feeling that when the body hits, the body A is doing some effect on body B is reacting and giving an opposite effect. And actually they are just, what we can see is, if we look in Newton's language, then action and reaction, they just imply mutual forces on interacting bodies. So, this gives a wrong impression that action is causing a reaction. There is no cause effect relation in Newton's third law. We just have a mutual pair of forces between bodies, and these pairs are this pair acts at the same time. So, there is no cause effect relation. Now, the other thing one can see is that if we consider motion of A and B separately, that means I am looking at this body A and there is a body B which is very close to it, it touches it, it applies a force. When I look at this motion separately, then on body A, FAB, the force on body A due to B, this is an external force. If we are looking at only body A. So, for example, let me draw, this is body A and I have FAB acting because B is coming and hitting the body. I look at body B, then I have FBA acting as an external force. This is external force on B. This is external force on A. But now, if we study A and B as one system, so that means now I am talking of body A and body B. Now, FAB and FBA, these forces are internal to the system. My system consists of both A and B together. So, these two forces are internal, and as you see, because they are equal and opposite, they cancel out. And now when I have to study the dynamics of A and B together as a system, then I will say there is no force acting, these two forces will cancel out. If other external forces are acting on A and B, let us say the weight or the reaction because of ground, then they have to be counted, but the interaction between A and B will cancel out. So, therefore, they are not to be counted, they are internal forces. And in some sense, then Newton's third law tells us that internal forces always are occurring in pairs. So, they act in pairs and they act on bodies and they cancel away in pairs. So, this is Newton's third law. Now, another thing which will happen when we talk of rigid bodies is, which we have not discussed here, we have said this is FAB, FBA. Newton's third law, when we take it in a bigger sense, when we extend it to from particles to rigid bodies, will also tell us that FAB and FBA, they are equal and opposite, and they act along the same line of action. And the reason why this gives us is because when we combine these two, then the total effect of these forces has to cancel. If they do not act along the same line of action, then we will realize that there can be a rotational effect of these forces if they act on different lines. So, therefore, these internal forces which we have said, they act on different bodies, they are, and their effect is they are equal in magnitude, opposite in direction, and they act along the same line. So, this is what is essentially Newton's third law. So, Newton's third law we will find will be particularly useful when we study system of particles, which means that in our subject matter of study there is not one particle, but two particles or three particles. And there when we consider the entire system as our unit of study, then the internal forces between various particles will cancel out. So, we will not even talk of these forces, and that is where we will find the major use of Newton's third law. Now, what we have seen is, let us sum up, we have seen Newton's first law, Newton's second law, and Newton's third law. Newton's first law was the law of inertia, and what we can see is essentially Newton's first law leads us to laws of statics. That is, if a particle is not moving, then sum of forces on the particle must be equal to 0. So, Newton's second law, which we have studied, essentially we will see it being written generally as F is equal to ma. This is just one form. Actually, the law says F is proportional to the rate of change of momentum. Mainly this will be used when we talk of a single particle or more particles or rigid body, where we will use this F is equal to ma. And when we have more than one particles, then we have to keep in mind the force we are talking of is the force which is external to the system. And this comes because of third law, which says that mutually the forces between particles, they cancel out. They are equal and opposite. So, in a sense, Newton's second law is used when we talk of dynamics of a single particle. When we talk of a system of particles or a rigid body, then we are effectively using both Newton's second law and third law together, with the third law cancelling out the effect of internal forces, internal particles. And so, therefore, what we have to consider when we consider a total system of bodies is only the external forces. So, these are the three laws, and the other thing which we have to keep in mind is that when we talk of motion of a body, then this motion has to be seen with respect to an inertial frame only. Only then will Newton's laws be valid. If the motion is given with respect to a frame which is not inertial, then we will first have to convert it how this motion looks with respect to an inertial frame, and then apply F is equal to ma. In the next class, we will continue ahead. We will look at different forms of Newton's second law depending on whether F is constant, a function of time, a function of space, or a function of velocity. And so, we will have different formulations which will come, one of which we have seen, the impulse momentum formulation, and this will also lead to the work energy relations, and we will look at problem solving from there. Thank you.